Hi, I'm Dr. Courtney with the Quantitative Reasoning Center. Isaac Newton's famous book, The Mathematical Principles of Natural Philosophy, might as well be called The Mathematical Principles of the Art of War, because the nation whose officers are most highly skilled at applying those principles in quantitative problem solving usually win the war. Okay, today we're having a look at section 12.4, number 39, and the problem is to compute the torque in a given situation. So let's use the idea problem solving format where I stands for interpret. So basically we're given 60 Newton force, we're given the length of a moment arm, 18 centimeters, and we want to find the torque. So we want to use the definition of torque, and it's particularly important here that the torque is defined as a cross product to find torque from the force, moment arm, and angle. Alright, now the D in our problem solving format stands for develop, and we want to draw a picture and we want to make a plan to sort of map out the course we're going to take toward a solution. So just drawing the picture the best we can from the book. We have a horizontal line, we have a bicycle pedal, we have the moment arm or the shaft, and we have essentially a pivot point, and then we see that we're applying, the force is applied this way, we're applying a force to the pedal, and the magnitude of the force is equal to 60 newtons, and we're given a couple of angles. We're given the angle between the applied force and the horizontal as, we're given that, well, let's go ahead and change it. It's 70 in the picture, but let's go ahead and solve it for 60 degrees, and let's keep this one at 10 degrees. So we've changed the numbers a little bit so that you can still get the benefit of solving this on your own. So the idea, and let's go ahead and put the distance here. This is, the pedal is 18 centimeters long. Alright, so now our plan is to express torque, and let's give that the symbol tau, in terms of the force and the moment arm. And let's be careful to define this as the moment arm. And this is important because a lot of textbooks define torque as R cross F. And that's not wrong, but we need to keep in mind that the vector R in that context means the moment arm, it's not a radius. Sometimes, if the object happens to be going around in a circle, like a bicycle pedal, it's the radius of that circle, but that's not why it's R. It really does mean moment arm. Alright, and now once we have that expressed, then we can substitute in for the magnitude. We're not interested in the x, y, and z components of the vector or things like that. We're not interested in the direction. We're only interested in the magnitude of the torque. So there's a formula we can substitute in for, and then we can, we want to make our units consistent. and then we can sub in the numbers and solve. Alright, now to evaluate, we can recall that the torque is equal to the moment arm crossed with the force, and this is the cross product between the two vectors. But in this case, since we're only interested in the magnitude, it's the magnitude of the moment arm times the magnitude of the force times the sine of theta. And here we're given two angles, and we need to be careful because here the theta is the angle between the two vectors in the cross product. And now let's take a little care with our units, and let's also think about this angle. Here's the force vector, there's the moment arm vector, so the angle is the sum of those, so the angle in this case is 70 degrees. Let's also be careful because when you work in a physics problem, you need to do it in a consistent system of units. And most physics is done in the SI, or the metric system of units, where forces are measured in newtons and lengths are measured in meters. So we were given the moment arm as 18 centimeters, but we want to note that that's 0.18 meters. And the force, 60 newtons, and times the sine of 70 degrees. And I'll leave punching in these numbers as an exercise for the diligent student. And then how would we assess? How would we double check that this is the right answer? How would we double check, and how would we think about whether or not the answer makes sense? Well, when we get the magnitude of the answer, we're probably going to get something around, well, what are the units of the answer going to be, right? The units of the answer should be Newton meters, or some cases meter newtons. Doesn't really matter because we know that multiplication obeys the commutative property, but your units had better have both a Newton and a meter. Had you forgotten to convert the centimeters to the meters, you'd have centimeter newtons, which really isn't a proper SI unit of torque. And also we can think about the magnitude. It should be somewhere in the ballpark of 10 meter newtons. Not exactly, but if you're much, much smaller than that, or if you're 10 or 50 times larger than that, odds are you've made a careless error in your calculations and you need to revisit what you've done. So here's our solution to 12.4, number 39.